let us quickly recapitulate what we have been doing for the last few classes. So, we have been working out the eigenfunctions of the angular momentum operator, and we found that the three components of angular momentum do not commute. So, you cannot have a simultaneous eigenfunction for all three components, and you can have an eigenfunction with a set of functions which are eigenfunctions for only one of them. And we chose Lz as the privileged component. We are going to work in terms of eigenfunctions of Lz, where the z direction can be chosen arbitrarily. So, we are working out, and L square commutes with all three components of the angular momentum. So, we are working out simultaneous eigenfunctions of Lz. So, y ak is an eigenfunction of Lz with eigenvalue k. It is also an eigenfunction of L square with eigenvalue a. And the Lz operator was just the derivative with respect to phi, whose solution was e to the power I phi by h cross into k, where k was the eigenvalue, and the fact that this had to be unique, single valued for all values of phi, and phi greater than 2 pi is the same as phi starting from 0 again. So, this gave us the restriction that k was m into h cross, where m had to be an integer. So, the first thing that we found was that the z component of angular momentum had eigenvalues which were integral multiples of h cross, and the integer we denoted by m. And now then onwards we used m to denote the eigenvalue of Lz. So, when Lz acts on this function y, which is got two parameters a and m, Lz acting on it gives us m h cross into the same function, and m into h cross is the eigenvalue of Lz. This was the first thing. We had to also work out the theta dependence. In order to work that out, we defined two operators L plus and L minus. The role of L plus and L minus is as follows. L plus acting on YAM, we found that L plus and L minus were defined as follows. L plus was Lx plus ILy, L minus was Lx minus ILy, and the function of these two operators L plus and L minus was as follows. If so, what was the function of this operator? L plus, when it acted on YAM, it gave us a different eigenfunction of Lz with eigenvalue m plus 1. So, it increased the z component of the angular momentum by 1 unit of h cross. The eigenvalue of Lz here was m h cross. After L plus has acted on it, on this function, we get a new function, and this is an eigenfunction with eigenvalue m plus 1 into h cross. So, the eigenvalue of Lz has increased by 1 unit of h cross. Similarly, L minus reduced the eigenvalue of Lz by 1 unit of h cross. So, L plus and L minus were introduced, and then we found, so using these L plus and L minus, you could keep on increasing the z component of the angular momentum or decreasing it arbitrarily. But then we found that there were restrictions, and the restriction was that the eigenvalue of L squared and the eigenvalue of Lz m had to satisfy this inequality. The inequality being that m into m plus 1 h cross square had to be less than or equal to a, where m is the m into h cross is the eigenvalue of Lz and a is the eigenvalue of L squared. This basically arises from the fact that Lz is just one component of the eigenvalue, and L square is the sum of all three components squared, and one component obviously cannot be greater than the sum of all three components squared, square of all three components, right. So, we were led to the conclusion that m has got to have a minimum value and a maximum value. So, you cannot just keep on arbitrarily increasing m or decreasing m. There has to be a minimum value and a maximum value, and we used m1 to denote the maximum value, m2 to denote the minimum value. And if y a m1 was the eigenfunction corresponding to the maximum value of the eigenfunction of m, then if L plus acts on this, it should give us 0, because you cannot increase m anymore. So the action of L plus, which is to increase m, will give us 0. Similarly, if L minus, which reduces the eigenvalue of Lz by 1, if it acts on the minimum value, the eigenfunction with the minimum value of m, this should give us 0. So these two conditions were used, and to obtain the following relation between m1 and a and m2 and a. So we found that m1 had to satisfy this equality, m1 into m1 plus 1 h cross square was equal to a, and m2 into m2 minus 1 h cross square was equal to a. So the minimum value and the maximum value of m have to satisfy these two equalities. This tells us that m1 and m2 are the negative of each other. So m1 is positive, m2 is equal to minus m1, and if we call m1 some integer, m1 is an integer, if we call this integer L, the maximum value of m, if we call it L, then a turns out to be L into L plus 1 h cross square, okay, which is quite obvious from here. If we call m1 the maximum value of m L, then a is L into L plus 1 h cross square. And m can take all possible values from minus L, which is the minimum value, to L. So let me again summarize what this tells us. What it tells us is that the eigenvalues of L squared, let me put it here, eigenvalues of L squared can be parametrized by one integer, by one integer L, okay, and the eigenvalue is, so L square acting on y, I am going to put the L on top, m on the bottom, theta phi. So L square acting on this is going to give us L into L plus 1 h cross square y L m. Okay. Y is the eigenfunction. The parameter L parameterizes the eigenvalues of L squared. Okay. Earlier it was being done by A, but we found that A has to be equal to L into L plus 1 h cross square, where L is some integer. So L is now parameterizing the eigenvalue of L squared, and this parameter appears on top, and L square acting on this gives us the eigenvalue L into L plus 1 h cross square, and L could be any integer. So L could be any positive integer, so L could be equal to 0, 1, 2, 3, 4, any possible integer. L is called the total angular momentum quantum number. And for a particle in a spherical potential well, in a spherical potential, the angular momentum is conserved, so this quantum number is also conserved. It does not change as the time evolves. If the expectation value of this quantity of L square does not change. So if it is in one eigenstate, it remains in that particular eigenstate. Okay. the eigenvalue of Lz are m h cross y l m, and m can be any integer from minus L to L, and m is called the azimuthal quantum number. Azimuthal quantum number. Okay. We also saw that the expectation value of any component of the angular momentum is conserved. So if this particle is in one eigenstate of with a particular value of m, it remains in that eigenstate in a spherical potential. Okay. So this is also conserved. If it is in an eigenstate with a fixed value of m, it is also conserved. Let me just give you a kind of classical interpretation of the whole thing. So we can think of the angular momentum vector being a vector of magnitude. This is you can think of it as a vector of magnitude L into L plus 1 h cross, and this has got several possible z components which run from minus L to L. So this is capital L. The total angular momentum you can think of as a vector. This is a kind of classical interpretation which is not exactly precise, but it gives you a kind of visual idea of what is going on. So for a particle in a certain state with a fixed value of small l, you can think of the angular momentum as being a vector with magnitude. See, L square has got eigenvalue L into L plus 1 h cross square. So L you can think of as a vector of magnitude L into L plus 1, the square root of it, into h cross. A vector with this magnitude which can have different z components which run from minus L to plus L. So let us consider a situation where, for example, L is equal to 2. If L is equal to 2, then you can think of the angular momentum as a vector of magnitude square root of 6 h cross. So the quantum number L equal to 2 you may think of as representing a situation where the angular momentum has a value this much, and it can have different possible orientations. The z component, if this is the z direction, the angular momentum vector can have different possible orientations. One is this is equal to 2, this is 1, this is 0, this is minus 1, this is minus 2. So you can visualize the angular momentum as a vector of this magnitude and having different possible z components. One possibility is z component of 2 into h cross, another possibility is 1 into h cross, 0 h cross, minus 1 h cross, and minus 2 h cross. Now in each of these states, the z component of the angular momentum is very precisely defined. If I make a measurement of the z component of the angular momentum for this vector, I will get 1 h cross. But the x and y components are not well defined, not precisely defined. So there is a probability of getting some value of Lx, there is a probability of getting some value of Ly. So you can think of this as that this actually lies on a cone. Each of these lies on a cone. And when you measure the x or y component, you can get any possible projection, okay, on the xy plane. And so this corresponds to different probabilities of getting different components in the x or y direction. So this is a kind of classical visualization which you can keep in your mind for this these results. Okay. So now, these are the possible allowed quantum numbers. So now we are still left with the problem of working out the function y theta phi. We have worked out the phi part of that function. We still have to work out the theta part of that function. Okay. Now the theta part of that function can be easily worked out. Once if we can work out these functions can be easily worked out if we can just work out one of them for a fixed value of L. If we can work out one for one particular m, if you can work out this function, you can obtain all the other functions by acting with L plus or L minus. So if you can just work out one of these functions for a fixed a and m, you can work out all the other ones by just acting with this or this. Okay, so this is the method which is applied to work out these functions. So in order to do that, we need to know the coefficient, no sorry, not we have, right. So you can just, if you know y a m, you can easily work out y m a m plus 1 by just acting with L plus. Similarly, if you can also work out y a m minus 1 if you know y a m. So for a fixed value of a and m, if you can work out one function, you can work out all the function for all the other values of m. So we are going to use this to work out these eigen functions. For that we need to know this coefficient c also if you want to preserve the normalization. So let us first work out what this coefficient c is. Okay. So in order to work out what the coefficient c is, we have to use this relation over here. We have to use these two relations as well as the fact that L plus will raise it and L minus will lower it. L plus will raise it and L minus will lower it. So let us first work out what is C plus, where C plus is defined over here. So if I act with YLM with L plus, it will give me YL m plus 1 with some coefficient C plus. I want to work that out. Okay. So L plus acting on YLM will give me C plus YL m plus 1, and we want to determine what is the value of C plus, of this coefficient which appears over here. So if this is normalized, then if we can find out this coefficient, then the resulting YL m plus 1, if you want to keep this also normalized, then you require to get this coefficient and divide it over here. Okay. So the way we go about doing this is as follows. We know that we use this relation over here. So what this gives us is that L square minus LZ square minus H cross LZ is equal to L minus L plus. Now let us take the inner product of this with YLM and YLM on this side. Let me write it out again. L square minus LZ square minus H cross LZ is equal to L minus L plus. And let me take inner product of this with YLM and here also YLM. Let me also put it here YLM. So this operator, these two operators act on this, and this whole set of operators act on this. Now this L squared acting on YLM gives us, all of these give us a H cross square outside, so I can write H cross square over here, and this gives us L into L plus 1. Each of these are normalized, so the inner product is 1. So this gives us L plus 1 minus this gives us m square and this gives us m. So, that is m into m plus 1 and this is the inner product of L plus acting on y L m with L plus y L m because the L plus and L minus are the conjugate of each other, and the right hand side is equal to C plus mod squared. The left hand side can be simplified. So, the left hand side becomes h cross square and this we can write as L square plus L minus m square minus m. Here we have L square minus m square. So, let me simplify this a little further. C plus mod square is equal to h cross square L square minus m square. So, this I can write the first L minus m, L plus m, this is L square minus m square, and I have plus L minus m. The final result is that C plus is equal to square root of, so I can take L minus m common, L minus m, and what I have is L plus m plus 1 into h cross. So, this is C plus. There could be some arbitrary phase over here which I have set to 1. Let me also work out what is C minus. So, C minus is defined as follows: L minus acting on y L m gives us C minus y L m minus 1. So, if you know y L m and you want to work out y L m minus 1 and we want to make both ensure that both of them are normalized, we need to know this coefficient here. So, this is worked out in exactly the same way. So, let me do it here. It will not take very long. So, the relation to use is L square. So, we are going to now use this relation over here, which gives us L square minus Lz square plus h cross Lz is equal to L plus L minus. We again take inner product with YLM. So, YLM here and YLM here. Similarly, here we apply YLM and YLM. Now, here you can guess what the right hand side is going to be. Right hand side is going to be C minus mod squared and the left hand side is going to be, I can take h cross square common, and here I have L into L plus 1, here I have minus m square, and now I have plus m. So, this I can write as C minus mod square is equal to h cross square into L minus m, L plus m, this is L square minus m square, and now I have plus L plus m. So, I can what I get is C minus is equal to h cross square root of, I can now take L plus m common, and what I have is L minus m plus 1. Okay. So, we have now obtained both the coefficients C plus and C minus. We shall use these later on. So, this is C minus and this is C plus. The plus sign and the minus, the plus and the minus sign get interchanged when I calculate, when I use for C minus, right. Just note the difference. There is a minus sign here, there is a plus sign here, there is a plus sign here, a minus sign here. Okay. So, let us, now that we have derived this, we will keep this aside and we will use it later on when we want to calculate the different YLMs. Now, let us start our calculation of the different the theta dependence of this function. So, we proceed as follows. We consider the function y, eigenfunction YLL theta phi. For this, in this function, m has got the maximum value which it can have, which is plus m. So, L plus acting on this should be equal to 0. So, if we can solve this equation, we can obtain this function YLL theta phi, which is exactly what we did in the simple harmonic oscillator. If you want, when we wanted the ground state, we acted with the operator A, which lowers the eigenvalue. Acting on the ground state, it gives us 0, which gave us a differential equation, the solution of which gave us the ground state. So, we use the same technique here. L plus acting on this should give us 0, and if we can solve this equation, we get the ground state. In order to do this, we need to know the operator L plus in the spherical polar coordinate system. So, what is the operator L plus in the spherical polar coordinate system? That is the next thing. So, let me get the expression for Lx and Ly. So, these are the expressions for Lx and Ly, and L plus is obtained by multiplying this by I and adding it to this. So, let me work out what is L plus and what is L minus first, and then we shall come back to this. So, L plus is equal to Lx plus I Ly, which is equal to Lx is I h cross cos sin phi del del theta plus cot theta cos phi del del phi. This is Lx, and I have plus I into Ly. So, I have I into minus I h cross into Ly, which is cos phi del del theta plus cot theta sin phi del del phi. Now, so we have to combine both of these. So, let us see how we can put it all together. The coefficient of this is I into minus I, which is 1, into h cross into, and we have cos phi here, plus I into sin phi. So, we can combine both of these and write it as e to the power, so I phi. So, this is equal to h cross e to the power I phi del del theta. So, this gives us the cos phi over here and I sin phi over here. We have cot theta in both the terms. So, we have plus cot theta. Now, here we have I into cos phi, and here we have minus, no, we have, so here we have I into cos phi, and here we have sorry, there should be a minus sign here, not a plus sign. Ly has a minus sign over here. Okay, so this is I into cos phi, and here we have minus sin phi, which is nothing but which is what I get if I put a I here into del phi, because this will give me cos phi into I. The real part of this is cos phi. If I multiply it by I will get this term, and the imaginary part is I into sin phi, which into another I will give me the minus sign. Okay, so this is L plus. Let us also work out what is L minus since we shall need both of them later on. L minus is equal to, L minus is Lx minus I Ly. So let us also work this out. This will be I h cross cos phi del theta plus cot theta sin phi. Rather it is, okay, now I have got it inverted. So let me just L minus is equal to Lx minus I Ly, and this is equal to I h cross sin phi del theta plus cot theta cos phi del phi. Then I have minus, and I have minus I into I h cross, minus I into minus I h cross here. So minus I comes from here, minus I h cross comes from the definition of Ly, and then I have cos phi del theta minus cot theta sin phi del phi. Now let us put this together. So what is the coefficient of del theta? So the first term will be, there will be a h cross outside, and here we have I sin phi, and here we have, so the minus sign and the minus sign go away. I and I give us another minus sign. We have cos phi over here. So what we have is minus, let me write it down explicitly, then we can all put it all together. So what we have is minus cos phi from the two i's, and plus I into sin phi. Del theta. This is the first term. The second term will be I, this is the first term, the second term will be plus cot theta, and now we have I into cos phi, I into cos phi over here, and this will give us, we have a minus sign, overall minus sign over here, which comes from the two i's, and the minus sign here will cancel out. So I have plus sin phi del phi. So this is equal to, so this gives us h cross with a minus sign over here, e to the power minus I phi, which gives us the first term over here, because e to the power minus I phi is cos phi minus I sin phi, and if I multiply it by minus I get minus 1, I get this thing over here. And I have to also, so this is into del theta. Okay, and now I have to get the second term. The second term is, so there will be a cot theta So what this gives us is, so I have to get the, so there will be I over here, and there will be a minus sign. Okay. So, this will give us cos phi into I and my plus sign, yeah. So, this is correct. So, cot theta into del del phi. So, we have obtained both L plus and L minus in the spherical polar coordinate system, and now let us go back to the equation which we had set out to solve, which is this. So, the equation, so we see that the equation which it has to satisfy, this has to satisfy is so L plus is over here. So, what the equation which YLL has to satisfy is that this operator, when it acts on this, should give us 0. Now, the action of del del phi on this is very easy to work out because we already know the phi dependence. The phi dependence is e to the power I into L into phi. M is L over here, right. This is the particular case where m is equal to L, the maximum value. So, the phi dependence is just, so the phi dependence is e to the power I L into phi of this function, right. So, if you differentiate this with phi, you get I into L, which will multiply this over here, and what this will give you is that you will get a minus sign over here and into L. So, this operator, these constant coefficients do not matter. This operator acting on this function gives us the following. It gives us del del theta minus L cot theta for IL phi into, yeah, this is it, into YLL is equal to theta phi is equal to 0. Right. So, we have to find a solution to this equation, and we know the phi dependence already. So, we do not have to bother about the phi part. The theta part can now be easily written down. So, I will just write down the solution, which can, this is now an ordinary differential equation in theta and the solution can be easily worked out, and the solution is, I will just write down the solution, y L L theta phi will be some arbitrary constant which we do not know as yet. This will come from the normalization, this into e to the power I L phi into sin theta to the power of L. If you differentiate this with respect to theta, then you will get sin theta to the power of L minus 1. Let us just do it. So, the theta derivative of this we can easily check. Theta derivative of sin theta to the power of L is equal to L into sin theta to the power of L minus 1 into cos theta, which is L into sin theta to the power of L into cot theta. I have divided and multiplied by sin theta. So, if I multiply by 1 sin theta, I will get sin theta to the power of L. I divide by sin theta, I get cot theta, which will exactly cancel out with this over here, because it is the same function. Okay. So, now we have obtained what is YLL. YLL is e to the power I L phi into sin theta to the power of L with some arbitrary coefficient, which is the normalization coefficient. So once we know YLL, we can easily now work out YLL, Y. So once we know this is the eigenfunction corresponding to the maximum value of M, which is M is equal to L. Now if we act with L minus on this, we will get the eigenfunction with the eigenvalue which is just one lower than the maximum. So L minus acting on YL L theta phi will give us C minus into YL L minus 1 theta phi. And we can act with it twice, 3 times, etc., and get the eigenfunctions corresponding to the smaller and smaller values of M. Now we are not at present bothering about the normalization coefficient. This is just a normalization coefficient. So we are not bothering about it. We are not working out what the normalization coefficients are. We are just working out the theta and phi dependence. So we shall not bother about the normalization coefficient right now. Okay. So L plus, this is L minus. So the operator L minus is over here. L minus is del by del theta into minus I cot theta del by del phi. And we are only going to act with this part of the function. We are not going to bother about the constant coefficients, which we shall fix later on. So y L L minus 1 theta phi is equal to, so the first term which we have is e to the power minus I phi, and then we have del del theta minus I cot theta del del phi into e to the power I L phi into sin theta to the power of L. So this is acting on this, and there will be some normalization coefficient which we are not putting in as yet. You should bear in mind that. Okay. So the phi part, the phi derivative acting on this will give us IL, and this whole thing becomes plus L, and then I can remove this function out of this whole thing. So this is equal to e to the power I L minus 1 phi, which is what we expect, right? The value of M now is L minus 1. So we expect e to the power I L minus 1 phi. Phi dependence is here, and we have del del theta plus L cot theta into sin theta to the power of L. So this is the function y L L minus 1 theta phi. Now this operator over here can be further simplified. So let me write that. So this will be equal to e to the power I L minus 1 phi, and this operator over here can be written as 1 by sin theta to the power of L minus 1. Let us fix the value just a little later, okay, into del by del theta acting on sin theta to the power of L into sin theta to the power of L. Let us see what happens if we act with this on this. So, del by del theta can act either on this or on this. When del by del theta acts on this, this will cancel out with this and it will give us del by del theta acting on this, which is the first term. When del by del theta acts on this, it will give us L, which is here. It will give us a cos theta, which will cancel out with this term over here. No, which will it will give us a cos theta, which you can combine with one of these sin thetas to get cot theta. What will remain is sin theta to the power of L minus 1. What will remain here is sin theta to the power of L minus 1. So, that will give us, that will also cancel out. Okay. So, this will give us the cot theta term. When you differentiate this, you will get L, you will get sin theta to the power of L minus 1 into cos theta. One of those cos thetas will combine with this, one of the sin theta from here to give us cot. What remains here will be sin theta to the power of L minus 1, which will cancel out with the sin theta to the power of L minus 1 in the numerator. So, we find that y L L minus 1 theta phi, this can be written as, okay. So, okay, so we can write it, we will leave it like this, okay, or we can just simplify it one step. I L minus 1 phi 1 by sin theta to the power of L del by del theta sin theta to the power of 2L. Okay. So, this is y to the power y L L minus 1. Now, we can work out y L L minus 2 by a similar procedure. This is equal to L minus acting on y L L minus 1 theta phi. Okay. So, we shall continue, we shall work this, evaluate this in the next class, and then we shall obtain general expressions for these eigenfunctions, and we shall also work out the normalization coefficients in the next class.